So we are continuing with our topic, electrochemistry. But for today particularly, we shall look at only an introduction to electrode potential, and then electrochemical cells. I'll introduce you to what we call electrode potential. You've heard about the word potential difference. So when you talk of electrode potential and potential difference, there is something common. I'm bringing the potential difference because it's a common term to those who do physics. And when you talk of electrode potential, people get confused. But you shouldn't get confused. How does electrode potential arise? Let's assume we have a metal rod. This is a metal rod. And that metal rod is for any given metal. Let the metal maybe be copper metal. This metal rod usually has metal ions in its lattice. If I pick just a portion here and try to show you the structure of this metal rod, this is what actually happens. It has copper 2 ions. Copper 2 ions in it. And a sea of delocalized electrons, 2 electrons for each ion. That's what is entirely the structure of that metal rod. It has metal ions and a cloud or a sea. People call it a sea of delocalized electrons. Now, when you dip this metal rod in a solution, this is the metal rod, you dip it in a solution of its ions. Let's assume you've dipped it in a solution of copper 2 sulfate. And the metal rod is copper metal. Some of the cations I've talked about dissolve. Some of the cations tend to dissolve in that solution. And when they dissolve, remember we said the metal has a sea of delocalized electrons and cations. When some of the cations dissolve, they tend to leave up an excess of electrons on the surface of the metal. So what is the result of that happening is that in this solution, you have very many ions. Some of them already in the solution, others dissolved from the metal rod. And that means that since the ions are dissolving, there are going to remain very many electrons on the surface of this metal. Electrons are negatively charged. That's why you see me putting in negative charges. Now this metal is going to become negatively charged with respect to the solution that is surrounding it. That tendency of the metal rod to lose ions into the solution, tendency of the metal rod to lose ions into the solution is called electrolytic solution pressure. You're now getting new terms. The tendency of a metal rod to lose some of its ions into its solution, a solution of its ions. Tendency of the metal rod to lose some of its ions, again into a solution of its ions, is what we call the electrolytic solution pressure. When that happens, the metal rod becomes negatively charged with respect to the solution that is surrounding it. And then we end up having this solution as a solution of the metal ions. Then alternatively, you have the metal ions, these ones here. They may take up the electrons on the surface of the metal, such that this reaction occurs. Because there are so many electrons on the surface of this metal here after the dissolution of the ions. So alternatively, we may have the copper ions taking up those electrons to deposit copper metal. In this case now, the metal is going to become positively charged. Why? Electrons are taken up. Electrons are being taken up. So most of the metal now becomes positively charged in that case with respect to the solution. The tendency of the ions to deposit on the metal from a solution, for it is called the deposition pressure. Now in solution, the electrolytic solution pressure, which I've just explained, and the deposition pressure occur simultaneously for a metal rod. They occur simultaneously for a metal rod. And the potential difference gets established. That potential difference between the strip of the metal and the solution depends on the nature of the metal and the concentration of the ions in equilibrium with the metal surface. So I've already given you an example using the copper rod. If you dip a copper rod in a solution of copper 2 ions, the copper rod gains a negative electrode potential because it has a greater tendency to dissolve from ions. Or it has a greater electrolytic solution. I mean, the copper rod doesn't act as the zinc rod. We shall look at the zinc rod also, but when you dip a copper metal in its solution, the copper has a greater tendency to be deposited on the rod than dissolution. So that implies that copper has a greater deposition pressure than the electrolytic solution pressure. It has a greater tendency to get deposited on the metal rod than a tendency for the ions to dissolve in the solution. And therefore it gains what we call a positive electrode potential. I think I need to explain this in detail. I've told you what happens when you dip a metal rod in solution. The first case could be the ion is dissolving from the rod into the solution. When those ions dissolve, the metal remains negatively charged. That's one case. The second case, we could have the ions in the solution picking up electrons. When they pick up electrons from the surface of the metal now rod remains positively charged because electrons are taken away. And we have just said that this one is called the electrolytic solution pressure. And the metal becomes negatively charged with respect to the solution. This one is called the deposition pressure. Why do we call it deposition pressure? Because the reaction occurring is this reaction. Copper is getting deposited. In the electrolytic solution pressure, We have the copper metal, the copper rod dissolving to give us copper 2 ions. So for the copper rod, it has a greater tendency to get deposited on the rod than to dissolve in the solution. And such metals that have that tendency get what we call a positive electrode potential. If they have a greater deposition pressure than the electrolytic solution pressure. And that's why the copper rod is usually called a positive electrode. For the zinc rod, it's the opposite. For the zinc rod, you will have it dissolving as well, or you may have the zinc ions getting picking up electrons from the metal depositing zinc. However, for zinc, it has a greater tendency to dissolve than to get deposited. And therefore, zinc gains what we call a negative electrode potential. It has a greater tendency to form ions, greater electrolytic solution pressure, and a smaller tendency to be deposited as a metal, lower deposition pressure. That's why zinc is called a negative electrode. I'm trying to give you the background to what we call electrode potential before we reach there. Now, whenever there is dissolution and deposition of the ions and deposition of the metal on the rod, usually an equilibrium gets established. So for zinc, we have this kind of reaction. The zinc rod dissolves to form zinc ions. But in the same solution, we also have the zinc ions depositing zinc metal, and equilibrium gets established. And the position, whether there is a greater tendency of deposition or a greater tendency of electrolytic solution pressure, depends on which metal we are using. So the position of the equilibrium, whether it lies to the left or right, depends on different metals. Some metals have a greater deposition pressure, others have a greater electrolytic solution pressure. As I've seen for zinc, I've told you zinc has a greater electrolytic solution pressure, hence a negative electrode potential, whereas copper has a greater deposition pressure, hence a positive electrode potential. Now that brings me to the term. I'm talking of electrode potential, potential. But what is electrode potential? We shall later see standard electrode potential, but I'm beginning with electrode potential alone. Electrode potential is the potential difference. This is the potential difference developed when or developed between a metal placed in contact with a solution of its ions. Simply that. The potential difference developed between a metal placed in contact with a solution of its ions. That's what we call electrode potential. Electrode potential usually has a symbol E. That is the symbol, and its units, usually it is measured in volts, which we call capital V. By IUPAC, according to IUPAC, Notation, electrode potential is usually a reduction potential. Electrode potentials that are most commonly given in books are reduction potentials, reduction electrode potentials. So in most of our work, we shall deal with reduction potentials. What is reduction? Reduction is gain, rig, and oxidation is loss, oil rig. Oxidation is loss, reduction is gain of electrons. So in most of our equations, we shall be dealing with this kind of equation, gain of electrons. Electrons on the left-hand side. Shall be dealing with the reduction equations, hence reduction electrode potentials. Because by convention, IUPAC suggests that electrode potentials that should be used should be reduction potentials. All right. Now let me introduce you to what we call the electrochemical series. This is not a new term to you. We looked at them in O level. Electrochemical series. You are aware this is an arrangement of elements in increasing order of electrode potential. In O level, we arrange them with a decreasing order or an increasing order of reactivity. Here we are arranging them in an increasing order of electrode potential. And I'm saying we shall use reduction potentials strictly. Okay? Now, we shall begin with the most reactive element, the element that has the most negative electrode potential. Remember, when electrode potential is negative, then it is high. And when the electrode potential is positive, then it is low. Okay, I first of all have the lithium metal. Lithium ion loses an electron, gains an electron from the lithium metal. That electrode potential is negative 304 volts. It is followed by potassium. Potassium has an electrode potential of negative 2.92 volts. Potassium is usually followed by calcium. I want you to be very careful here with the electrochemical series. Sodium doesn't come first. Let me ignore the states due to the space I have. So this one gives me calcium metal, and the electrode potential is negative 2.87. Calcium is then followed by sodium. Give me sodium metal. The electrode potential here is negative 2.71 volts. Magnesium follows. And magnesium has an electrode potential of negative 2.38. After magnesium, aluminium comes in. To form aluminium metal, the electrode potential here is negative 1.66. Manganese, a new element now from your O-level knowledge. You didn't look at this. After aluminium, we go to manganese. It has an electrode potential of negative 1.18. After manganese, we have zinc. Zinc has an electrode potential of negative 0.76, and manganese has negative 1.18. Did I write it? Yes. After zinc, chromium comes in. We didn't look at this in O level. Chromium negative, chromium is negative 0.51. After chromium, iron 2, and iron has an electrode potential of negative 0.44. I think you see the order here. From your O level, you didn't have lithium, then you had this order, you didn't have manganese, then you go to zinc, you didn't have chromium, you went to iron. After iron, you have cobalt. Cobalt is negative 0.28. After cobalt, nickel comes in. Nickel is negative 0.25. After nickel, the tin comes in. Tin is negative 0.14. Lead follows. Both of these are in group 4, the group 4 cations. Lead is negative 0.13. You see the difference, very small. After lead, then hydrogen. (0.00). Normally write electrode potentials to 2 decimal places. So since hydrogen has 0.00 standard electrode potential, we shall be using it as a reference electrode, such that we measure other electrode potentials with respect to it. So from the negatives, we come to hydrogen, and after hydrogen, we shall go to the positives. Below hydrogen, the first one is the tin 4 ion. The tin 4 ion forming a tin 2 ion. Tin 4 ion giving us a tin 2 ion. The electrode potential here is positive 0.15. After the tin 4 ion, we have copper 2. Copper 2 has an electrode potential of 0.15, equal to that of tin 4 to tin 2 ions. Okay, after copper 2, we follow that with, no, this one should be copper 2 forming a copper 1. Copper 2 forming the copper 1 ion. This is positive 0.15. But we also have the copper 2 ion forming copper metal. That one is 0.34. Positive. We also have the copper 1 ion forming copper metal steel. That is positive 0.52. We have iodine. Iodine is solid, giving us iodide ions. That one is positive 0.54. The more positive electrode potentials become, that means they are decreasing. Iron 3 ion to give us ion 2, the electrode potential there is positive 0.77. We have the silver ion forming silver metal. Electrode potential here is positive 0.80. We are writing it to 2 decimal places. Mercury, 2 ion, forming mercury metal. This one is a liquid. It's also positive 0.85. Bromine liquid, giving us bromide ions, 2 of them. Electrode potential here is positive 1.07. Manganese 4 oxide, hydrogen ions, 2 electrons, giving us manganese 2 ions. I'm using half arrows here because we talked of equilibrium being established between electrolytic solution pressure and deposition pressure. 1.23. Dichromate 6, 14 hydrogen ions, 6 electrons, chromium 3, 2 of them, 7 waters. This should be 2 waters. This is positive 1.33. Chlorine, 2 electrons, chloride ions, positive 1.36. Which element is that? Ce. Can anybody guess which element that is? Element with atomic with the symbol Ce, 4 plus. Okay, you can't guess, but that element is called cesium. That's the element. Cesium. Now cesium 4 plus plus an electron give us cesium 3 plus. This one occurs if the metal is dipped in sulfuric acid. That one is plus 1.45. We have the manganate 6. That's the manganate 6 ion. No, 7 ion. 8 hydrogen ions. Okay, manganate 6 ions, 7 ions, 8 hydrogen ions plus 3 electrons to give us manganese 4 oxide plus 4 waters. This one here is 1.52 positive volts. Then we still have the cesium ion 4 plus an electron, giving us still the same equation as the previous one, but in this case we have it in nitric acid. In that case, electrode potential is positive 1.61. Still we have, this was manganese, giving us manganese. This should be manganese 2 ions. And then we have the manganate 7. I think it is 4 hydrogen ions in this case. 4 hydrogen ions, 3 electrons, giving us manganese 4 oxide plus 2 water. Electrode potential here is positive 1.69. Last but not the least, hydrogen peroxide. 2 hydrogen ions, 2 electrons, gives us water. Electrode potential here is positive 1.77. And then finally, fluorine. 2 electrons, giving us fluoride ions. The electrode potential here is positive 2.87. That implies that fluorine has the most positive electrode potential, and lithium has the most negative electrode potential. Now we need to interpret these electrode potentials. What do they mean? If an element has the most negative, what does that imply? And if it has the most positive, still what does that imply? We need to understand those concepts before we proceed with this topic, such that you don't have challenges in the near future as we discuss the topic. When an element has a more negative electrode potential, more negative electrode potential, actually more negative reduction potential, that element is then highly electropositive, a very reactive metal. It is highly electropositive. Examples of such metals include lithium, potassium, sodium, magnesium. They are highly electropositive. And that's what you did in your O-level in the electrochemical series. You done with those elements and you say they are very reactive. So if you see it in terms of electrode potential, if they have more negative electrode potentials, then they are highly electropositive. If you come back here and you note this, you see that the most electropositive element known is lithium, followed by potassium, calcium, sodium, magnesium. In elements with more positive values of electrode potentials are highly electronegative. Look at this. Elements with more values of positive electrode potentials like fluorine is the most electronegative. Okay? Followed by which element? Followed by chlorine. Followed by bromine. We are looking at the elements, not compounds. Okay? So I think that idea is good. Elements with more positive electrode potentials. When you see a reduction equation written, an electrode potential is more positive, it implies that those elements, these are elements with that tells us that those elements are highly electronegative. And from our data, we have seen that fluorine is most electronegative, followed by chlorine, followed by bromine. Let me pick some two equations up there in the half cell reactions. I will pick this one, dichromate 6, giving us chromium 3 ions. Okay, dichromate 6 appears plus 14 hydrogen ions. I know you know how to balance these equations. Plus 6 electrons. This reaction gives us 2 chromium 3 ions plus 7 waters. The electrode potential for this reaction is positive 1.33. When you look at that equation, I want you to understand this. Any species, this is the left, and this is the right. Any species on the left, okay, any species on the right of the equation, so long as this equation is a reduction equation, it shows gain of electrons. Any species on the right of that equation is a reducing agent. And any species on the left is an oxidizing agent. I want you to note this carefully. Any species on the right is a reducing agent. Any species on the left is an oxidizing agent. How can you best remember this? In the reduction equation, right represents reducing. Right represents reducing agent. So if I ask you the reducing agent in this equation, the oxidizing agent first is the dichromate 6 ion. Dichromate 6 ion. In acidic medium, that's the oxidizing agent. And if I ask you the reducing agent here, it is the chromium 3 ion. And I cite for your question and ask you which is the reducing agent in that equation and which is the oxidizing agent. Okay. The dichromate 6 ion is being reduced. Why? It is gaining electrons. Any substance that is reduced is an oxidizing agent. You can also use that approach to understand that. That's another thing I wanted us to note. Let me have two equations now. I'm still bringing this one. Okay, let me pick some other two other than that one. I'm now picking the iron 3 ion plus an electron to give me the iron 2 ion. This reaction here, the reduction potential for it is positive 0.77 volts. I also want to pick one iron. I want to pick that one between the nickel 2 ion giving me nickel metal. The electrode potential for this kind of reaction is negative 0.25 volts. I want us to get a clue from the two equations given by this note. When you look at these equations, these two equations, this is the right and this is the left. Meaning all these pieces, this side, are they reducing agents or oxidizing agents? And nickel 2 is nickel metal and iron 2 iron. Reducing agents or oxidizing agents? According to what we have just discussed, right, reducing. So long as these are reduction equations, electrons are on the left-hand side. So in these equations, these two here are reducing agents. The iron 2 ion and the nickel metal are reducing agents, whereas the iron 3 ion and the nickel 2 ions are oxidizing agents. Oxidizing agents gain electrons. Now I want us to have another clue about information we can get from electrode potentials and equations. Any species on the right for a reaction with the lower or more negative electrode potential, that species is a stronger reducing agent. Look at the two values here. Which one is more negative? This one is more negative. Now that species on the right, the reaction with a more negative electrode potential is a stronger reducing agent than the species with a higher or less negative or more positive electrode potential. So this implies here that nickel is a stronger reducing agent than the iron 2 ion. Why? The standard electrode potential for the formation of nickel metal from nickel 2 ions is more negative than that for formation of the iron 2 ion from the iron 3 ion. That's why nickel is a stronger reducing agent than the iron 2 ion. Hope you're all getting me clear in that case. So we are looking at these two here being reducing agents, but which one is more reducing? The nickel is more reducing than the iron 2 ion because it has a more negative electrode potential. Now that implies that if we are looking at the electrode potentials to tell us the element with a more negative electrode potential or the most negative electrode potential is the strongest reducing agent. And when you go back to the electrochemical series, we see that that is lithium. Its value is most negative. That implies that lithium is the strongest reducing agent. Lithium metal is the strongest reducing agent, followed by potassium. And according to this, we see that the weakest reducing agent known is the fluoride ion. It is the weakest reducing agent, but the strongest oxidizing agent. I want you to get these ideas before we proceed with the topic. So we are saying that fluorine with a more positive electrode potential is the strongest oxidizing agent, and lithium is the weakest oxidizing agent. Lithium is the weakest, the lithium ion is the weakest oxidizing agent. So when you look at two values still, we can know which one is strongly oxidizing. These ones here are oxidizing agents. And for the oxidizing agents, it is the opposite. The ones that have more positive electrode potentials are more oxidizing. So when you look at these two, we have said nickel is the strongest reducing agent. But when you look at these two, the iron 3 ion is a stronger oxidizing agent than the nickel 2 ion. Why? The iron 3 ion, the reduction of the iron 3 ion to iron 2 ion has a more positive electrode potential than a reduction of nickel 2 ion to nickel metal. So there we see the more positive. If they are both negative, then we see the less negative. I think that is also very clear for you? Okay, so the more positive the electrode potential, the easier it is to reduce the ions on the left. So the metal on the right is relatively unreactive and relatively poor reducing agent. Now, I think you've got the idea of oxidation and reduction using electrochemical series and electrode potentials. Now, I will pick one electrode, the lithium electrode, which we saw that it is given as this. This is the reduction equation from the lithium metal. So similarly, the electrode potential here was given as negative 3.04 volts. We can write this half cell in this format. We can write it as the lithium. I've done a mistake here. This should be 1 electron and the charge should be 1. So the lithium ion half cell can be written as this. It can be written as lithium ion, lithium solid. We can use a stroke like that. That shows this process, the reduction process. And we normally follow it with negative 3.04. So we have summarized this equation in that format. It shows that the lithium ion is reduced to lithium metal, and the reduction potential of such a reaction is that. On your page 730, you'll have a question that summarizes all that I've talked about. Try to go through it and see if you can get the answers to that question.